Hi everyone, this is chapter 9 on descriptive statistics, significance levels, and hypothesis testing. So, quick overview of what these three concepts are, and then we'll look at them in more detail in today's lecture. Descriptive statistics creates summaries out of raw data, and when we say raw data, those will be the numbers that we collect from the surveys or questionnaires that we administer as researchers. So we can collect those numbers and then we summarize them so that our readers are able to understand what the sample is like and the results that came from the surveys. Significance level is the level of error that the researcher is willing to accept in the study. So it's the criterion for accepting or rejecting the hypothesis, and it is based on some probability, and we'll look at what those numbers would typically look like in communication research. We will also be looking at hypothesis testing, and as we recall, hypothesis testing is about testing variables based on some educated guess that there is some kind of relationship or difference among the variables, and not just any relationship or difference, but the difference and or relationship is statistically significant. So we'll tie all of these concepts together as well as things that we have read in previous chapters to help us understand how quantitative researchers use hypotheses and how they use the data that they collect in their studies. This slide tells us about how researchers will tabulate or compile the data that they collect. Recall from the previous slide, we talked about raw data, and this is how we manage those raw data. Essentially, most of the time, it can be the Excel spreadsheet where we can have columns, the columns representing variables of the study, whereas the rows of those Excel spreadsheets will represent the responses of individuals. So as we would have seen, oftentimes surveys will use a 7-point Likert type scale, and so the rows in the Excel spreadsheet can represent those responses that the participants provide on the Likert type scale from 1 to 7. So this slide just tells us how raw data will be managed or compiled by a researcher, not exactly critical or critically important for our understanding, just to know that how researchers manage the data and make sense of it. Here's an important concept for this chapter as well as for quantitative research. What is a normal curve or a bell curve? A normal curve or a bell curve is a theoretical curve that demonstrates the theoretical distributions of scores. So researchers who have done a lot of studies in many disciplines, they conclude that a normal distribution or a theoretical curve should look something like on page 159, figure 9.2, the top figure that you see right there, the normal distribution curve. The normal distribution curve is symmetrical, and so what is on the left side looks like a mirror image of the right side. If you are looking on page 159 on the first um, first table on figure 9.2, sorry, figure 9.2, that's right. It's a normal distribution because it demonstrates or shows that the majority of the responses, majority of the cases all happen in the peak of that curve. So let's take a look on our next slide where we can have a better view of what that means. So a normal distribution would look like this. Theoretically speaking, most of the cases will be right up here at the peak, and as we go down the peak on the right side as well as on the left side, we get fewer cases. So you see that on this end right here on the left, the curve is very, very close to the horizontal axis. Same thing on the right, the curve from the peak comes down and is very, very close to the horizontal line. Theoretically speaking, this curve continues infinitely and it never touches the horizontal axis. Why does it not touch? Because it's theoretical. It's theoretical that the number of cases on either extremes, either on the right side or the left side, will extend infinitely for a very, very long, in fact, forever. So the two lines never touch, will never touch. Okay, so this is a theoretical model. In reality, we are more likely to see responses plotted on a curve like this. If it's curved like this, we call it a positively skewed distribution, or it may curve like this where there are more cases on the right side, and if a curve looks like this, we call it a negatively skewed distribution. Okay, so the example that we see from the book tells us that, for example, communication apprehension will probably yield a curve like this, a positively skewed distribution. The example in the book given by the textbook author on page 160 on page 160 will tell us that if, for example, in a communication department when we are sampling, say, communication majors on communication apprehension, we are more likely to see that comm majors would report low levels of communication apprehension as compared to high levels of communication apprehension. So because in comm classes we spend so much time presenting, doing public speaking, we feel less stressful or we are less nervous about presenting. So when we ask people about communication apprehension, whether it's low, which is right here, or if it's high, which is on the right side, more likely than not, communication majors will say they have low levels of communication apprehension. So you see that there are more cases on the left side. It peaks relatively low over here, not quite in the middle, and then it declines. And of course, like all things in life, there will be some of us who are very nervous about presenting or doing communication, public speaking. Okay, so that is a positively skewed distribution. The book also tells us on the same page that if we are talking about communication competence among comm majors communication students in the comm department, we probably will see the opposite effect, which is a negatively skewed distribution. So again, on the horizontal axis, if the left side represents low numbers and it increases on the horizon, and we have high numbers over here on the right side, we know that in terms of communication competence among comm majors, more comm majors will probably rate themselves having higher levels of communication competence right here than some of us who may be either very modest or are still starting out in our major. So we have a smaller number of people who are right here on the left hand column, where we feel that we are not quite competent in our communication, but comm majors, because we do so many presentations, we feel more confident in our competence. So we have a peak that is further on the higher end of that continuum. Okay. In both of the positively and negatively skewed distribution, we see that the mean is right here, and then the mode will always be more extreme than the mean, as we see over here, the mode. Okay, so what do we do with descriptive statistics? Descriptive statistics are numbers that we collect during the surveys or questionnaires, and then we can summarize it for our readers. So it can be a number of cases. So you see on page 162 on the bottom, figure 9.4, number of cases we may note as a lowercase n or a uppercase n. Sometimes we use either of those, so doesn't quite matter which one that we use, lower or uppercase N. It means the number of cases, so it can also mean the number of people who participated. So you may have read articles that said we have 942 participants, for example. So instead of putting that in sentence, we might put lowercase n equals sign 942. So that tells us that that is the number of participants or number of cases that were reported in the study. We'll see that there are other measures that will report things like the central tendency, and that will be one of the things that we're talking about today as well. Central tendency refers to the mean, median, and mode, which is something that we probably are familiar with, having read those or used them in other classes. And in descriptive statistics, we can also demonstrate or to highlight for our readers the dispersion or variability. And when we talk about that, it is the standard deviation that we're talking about, and we'll see that in a future slide. So as mentioned earlier, number of cases, the small n or the capital N equal sign with a number tells us the number of cases or the number of participants of a study. So that's something good to know, because when you see a quantitative or qualitative paper and there is a small or lowercase or uppercase n, you know what the authors were trying to say. Okay, measurement of central tendencies. So I mentioned that is the mean, median, and mode. So a recap of what those things are. Mean, in layman's term, we call it the average. So we know that we just add everything up, divide by the number of cases, and that will give us the average. The median means that when we line up the scores, from largest to smallest, greatest to the biggest number to the smallest number. The one that is on the middle will be the median. If there are two numbers that are right in the middle, then we average the two, and that will be our median. Finally, what is mode? Mode is the most common score. So when we have the findings, the returns, the scores that we get from the participants, we rank them from highest to lowest, and then we can see which number or which response is the highest, use the most number of returns. That will be our mode. Measurements of dispersion or variability, well, that is something that we'll look at as the standard deviation. Sometimes researchers might just write lowercase s, lowercase d, and when we say standard deviation, it helps us to know how do the cases distribute or disperse from the mean. And we'll look in this curve, which will it will be in a better place to help us understand what standard deviation means. So recall that a curve like this, a symmetrical curve like this, is the theoretical normal bell curve that we talked about a few slides ago. Okay, here we have the mean, and we see that the median and mode are also right here. They're all right in the middle. When the mean, median, and mode are all in the middle, we know that this is our normal distribution curve, the theoretical curve. Well, here we have one standard deviation, within one standard deviation above or below the mean. We might also say it's within one standard deviation of the mean. What that means that of the cases that were reported in the research report, 68.26% of the cases fall within this part of the curve. From here, this +1 point, this part of the curve, all the way down to this part of the curve where it is -1. So within this curve right here, on the left and on the right of the mean, which is this thing right here, on the left and the right, we capture 68.26% of the cases right here. So the majority, 68.26%. If we say it's two standard deviations from the mean, So again, the mean is this thing right here in the middle, minus 2 over on this end, plus 2 on this end. Everything from plus 2 to minus 2 will be 2 standard deviations from the mean, and when we are within 2 standard deviations of the mean, we capture 95.44% of the cases. So 95.44% of the cases are within this part of the slope of the curve and as well as this part of the slope. Almost everyone is captured. Now if we say 3 standard deviations, we're looking at minus 3 to positive 3. So that will include this 2.14%, which is right here, this curve right here, and this 2.14%, which is this curve right here. Within 3 standard deviations from the mean, we capture 99.72% of the cases. So that's really, really high. It's not quite 100% because, as you remember, the theoretical normal curve, this darker line right here, it goes down very close to the horizontal axis, continues to extend, and it never touches the horizontal axis. So that very, very small percentage that we're missing here will always be down here, but we never quite capture all of them. So that's the normal distribution curve, and with that we learn about standard deviation, what that means in the normal distribution. So as a quick recap, if we say that the respondents or the cases are within 1 standard deviation, which is 68.26, we have an idea that the scores would capture this much of the cases. Whereas if we expand to say 3 standard deviations, we capture 99.72%, very, very high number, but not quite 100%. Okay, so when we report mean, we always report standard deviations as well, because it helps us to have an idea what the range is. So if we say that a standard deviation is 7, if you look on page 165, if we say that the standard deviation is 7 and the mean is 74.25, it means that within 1 standard deviation is plus minus 7 of 74.25. Meaning to say anything that is between 81.25 to 67.25, anything between those two numbers will be within 1 standard deviation of the mean. So that gives us an idea that 68.26% of the people will fall within that 81.25 to 67.25. More on descriptive statistics. Mean, median, mode are the central tendencies that we will report. What other things do we report? We might report frequencies as well. Frequencies just mean that the number of times something happens. So for example, how frequently do you eat chocolate in a week? So we might represent that average number with a lowercase f. And again, if an article says lowercase f equals sign 4, then you know that the frequency is 4. Percentages, we like to use percentages because we can then compare it to a complete number, which is the 100. Calculating, traditionally we can calculate those central tendencies using a calculator which has a square root function or the square root key, but these days we don't have to use a calculator or to manually write steps to find those central tendencies. We can quite easily use spreadsheets or statistical programs to run those numbers for us. So what this slide tells us is that traditionally, descriptive statistics, we will use a calculator and manually do our calculation either on a calculator or with conjunction with some writing on a piece of paper, scratch paper, and then combining steps. But these days, we don't necessarily have to do it by hand or by a calculator. We can just put it in a spreadsheet and let the computer do the job for us. All right, significance level, we talked about that a little bit at the start. It is the level that, as I alluded, the degree of error that the researcher is willing to accept in a study. So traditionally in communication and in most of social science, we will accept a 0.05 level as the probability level that we feel comfortable accepting. So what does the 0.05 mean? It means that out of 100 scores, 100 responses where they can be valid, there is a possibility that 5 of these 100 findings that appear to be valid are actually due to chance. Meaning to say, of those 100 that appear to be valid, 5 happened because it was pure chance. It was luck. We were lucky. There was no real demonstration that the hypothesis was supported. Those 5 cases just happened. It was pure luck. It was lucky. Okay. So if we say those 5 cases are lucky, then are we comfortable with that? Well, if we say that if it's a 0.05 acceptable level, then out of 100 cases, we are okay or we are comfortable with 5 of those 100 cases being just pure luck, pure chance, lucky that they got it. Okay, so that means that there's this room of error of 5 out of 100. As mentioned in the previous slide, 5 out of 100 cases that appear to be valid were actually due to chance, so pure luck. Significance level can also be demonstrated or called the alpha level or just simply the lowercase p. Okay, if the finding yields a p level that's greater than 0.05, we will say that the finding is non-significant. It is statistically non-significant because if the p-value is more than 0.05, that means more than 5 out of 100 cases, findings that appear to be true or valid were actually due to pure chance. So that's a pretty high rate if it's more than 5 out of 100. So in communication, social science research, 0.05 is what we typically accept, but if it's 0.01, it will be better. If it's much better, if it's 0.001. Okay. So again, if the alpha level is equals to or lower than 0.05, we say that the finding is significant or real. In other words, the finding is statistically significant. Hypothesis testing is the testing of variables because we made an educated guess that the variables had some kind of relationship or there is some meaningful difference between the variables. So once we have our variables and we want to make the experiment to test or any kind of procedure, any kind of design doesn't have to be experiment to determine if the relationship or the difference exists, we will test our hypothesis. We'll see that while we are testing the alternative hypothesis, which is what we see right here, in reality, what we are trying to do is that we're trying to reject the null hypothesis. So the hypothesis testing is to one or the other, either to accept the alternative hypothesis or we're trying to retain the null hypothesis. Okay, remember that the alternative hypothesis is the opposite of the null hypothesis, and the alternative hypothesis is the one that we typically see in academic papers. When we present the hypothesis, we just say hypothesis instead of saying alternative hypothesis. Okay. When we test hypothesis, we're trying to statistically test the null hypothesis, and the idea is to see if the findings meet the significance level that we predetermined before we run the test. Remember that we talk about the alpha or the p-value being the bar that we determine if a hypothesis will be accepted or not. So we are comparing the p-set value that we set prior to the study being conducted to the p-value or the alpha level that we produce through the statistical test. When we run the hypothesis and we look at the p-value from the test, this is what the researchers have to determine. So, if the hypothesis is supported, and what that means is that the relationship exists or the difference exists. When the hypothesis is supported, we should make the conclusion of decision 1, which means that the null hypothesis is demonstrated to be false and therefore is rejected because hypothesis is supported. So the correct decision is to make a decision 1 if the hypothesis was supported. Okay, but if the hypothesis was not supported, then we should do something else. If the hypothesis is not supported, we should retain null. And when we retain null, that will be the right choice. But then if the researcher were to reject null in that situation, then the researcher committed a type 1 error, even though null is true or null should be retained. Okay, so again, if the null hypothesis is true, but the researcher rejects it, then that is a type 1 error. In other words, if the null hypothesis is true, the alternative hypothesis is not true. And by committing type 1 error, we're saying that a not true alternative hypothesis is true. So that's a false statement, a false conclusion. What about decision number 2? Okay, when the hypothesis is not supported, null must be retained. So that is the correct decision, and that will be decision 2. Okay, when the hypothesis is not supported, null hypothesis must be retained. However, if null is retained instead, even though it is false, then that is a type 2 error. If null is retained instead, even though it is false, then it is a type 2 error. What that means is that the hypothesis is correct, is established, but instead of rejecting it, as in rejecting the null, if the researcher retains a null, then the researcher commits a type 2 error. Okay? So chapter 9, the most complicated concept will be the type 1 and type 2 errors. And how do we make those conclusions about type 1 and type 2 errors? You can use this table to help us determine which will be the correct conclusion, which is the the decision 1 and the decision 2 in both situations, and where type 1 error and type 2 errors are committed. And we can make the assertion of whether it's one of these 4 based on the hypothesis testing, and the hypothesis testing is based on the significance level, or the alpha or the p-value. So all of those refer to the same thing: the p-value, the alpha level, as well as the statistical significance. Those are referring to the same things. So that would conclude chapter 9.